Can you hear me better now?
Oh, yeah. Can you hear me okay?
Yeah, my headphones were off. The audio out was streaming through the room, but the microphone was in my bag. And
Got it.
you're lucky you don't have to see how cold it is right now.
Yeah, it's so cold outside.
No. Still there?
Yep, I'm still here.
Yeah.
All right, well, let's get started. So welcome back to all you brave souls who went out in the 1-degree weather, and hello to everybody who is live streaming now. I hope you guys are having a good first week and finding your way through classes and getting settled into everything. Just a couple quick reminders before we get started on the content. Your first graded quiz is due on Sunday, so that's 1.3. That's what we'll be working on today. And your first 2 homework assignments are also due on Sunday. So 1.1, which is the stuff we covered last time, and 1.3, the stuff covered today. As you work on that, if you find that you are getting stuck or need help, definitely utilize the drop-in help to ask questions. So the links and times are all posted in Moodle for you. And there's times today and there's some times on Sunday that people are available and can help you with any of that. Additionally, there's going to be 2 review sessions to cover some of the algebra that is on the algebra review worksheet. The first one is going to be today from 5 to 6 p.m. I posted that link on Moodle with William. So if you tried the getting started algebra assessment and you think it would benefit you to just review some of those algebraic ideas, you don't need to sign up or anything. You just pop on at 5 o'clock tonight and William will go through those. He's also going to run the same session on Monday at 4 o'clock, and that link is also in Moodle. So if you think that will be beneficial to you, definitely check that out. After Monday's session, we will post a recording of that workshop. So if you're not able to attend either of those, you can check out the recording. So other than that, I don't think there's any big announcements right now. A couple of you have emailed me about Wiley. There are instructions posted in Moodle that shows you which product to buy. So make sure you're using that to get registered. And then if other issues come up, you can certainly stop by drop-in help and we can try to troubleshoot, or you can send me an email. One of the easiest ways to fix things that happen in Wiley is just to try a different browser. Some browsers are more compatible than others. So I encourage you, if something's not working right, if something's not loading, just try a different browser because sometimes that will fix whatever the issue is. Okay. All right. So today we're going to be jumping into 1.3, which is rates of change. And so this is sort of where we start building the ideas of calculus. And so I will sort of allude to some of the parts that we will revisit later. But we're starting our foundation of the course with this rates of change. There's 2 types of rates of change we're going to look at today, something called the average rate of change and then the relative rate of change. The average rate of change is going to be a much bigger part of what we do, but we want to make sure we can distinguish between the 2. Okay, so I'm going to go ahead and turn on the dot cam here. And again, if you're interested in having these printed out, these PDFs are all available on Moodle, so you can certainly print them out ahead of time if you want to have them to write on, or if you have some sort of tablet, you can download the PDF and ink on that. Okay, so when we start thinking about this, you know, we really want to start with this idea of what is calculus, right? So we're in calculus 1. What does that even mean? And so when you boil it down to sort of the very, very most basic way we can talk about it, calculus is the study of change. So we're interested in how things change, how quickly they change, why they change, right? That's what we're interested in. We're looking at how and why they change, what that tells us, and what that means in sort of a real world context. So when we start this, the way that I typically work in math is that, we take what we know and we use that to figure out what we don't know. Okay, so the thing that you are assumed to know that we are going to build the entire course upon has to do with what is a linear function. Okay, so I'm sure that you are familiar with this. So linear functions are functions that are of the form y equals mx plus b, right? There's another form you can write it as y minus y1 equals m times x minus x1, slightly different, but it's the same formula, just rewritten. So that's what we're building upon, right? This idea of a linear function. And one of the key things we're going to be working with is the slope. So the slope is the m in our equation, and the slope tells us how much the dependent variable changes for every 1 unit that we change the independent variable. So you may hear things like rise over run, change in y and change in x. There's a lot of different ways that we think about the slope, right? So you may have seen change in y over change in x. You may have seen something like y2 minus y1 over x2 minus x1, right? You may have seen rise over run. So however you learned about how to calculate slope, what we're doing is we're considering how much the dependent variable changes when we change the independent variable, and we're scaling it to see what that changes when we change it by 1 unit. Okay, so we're really interested in building upon slope. That's where we're starting. That's the thing we are assumed to know. Okay, and so when we know something, we're going to use that to try to learn about all sorts of other things. We take what we know to try to figure out what we don't know, and then we keep trying to make it better. That's sort of our process, okay? So in a linear function, right, the function that we're looking at is a line, right? Which means it might look like this. That's a linear function. It could look like this. That's a linear function. Right? It could be horizontal. You could have something that looks like this. That's a linear function, but they all are lines. Okay. So the first sort of thing that we need to know about rates of change is if your function is linear, okay, then the rate of change is the slope. Okay. So when you know the slope of the line, that is the rate of change of that function. So that one we already know because we know how to find slope. So we just need to apply that, and that is the rate of change. The question then becomes, what if we want to start to measure the rate of change of a curved function or a nonlinear function, right? How do we do that in a way that makes sense when we have this curve? Right? So one thing that we are not going to do is we are not going to use geometry, right? We're not going to use arc lengths to try to figure it out. That's a different type of course and a different type of analysis. So what we're going to do, again, is we're going to take what we know, which is linear functions, and use that to figure out what we don't know, which is how to figure out the rate of change of a curved function. So what we're going to do is we're going to retrofit a line into our curved function to start to talk about this. So what does this mean? The first thing is we need bounds, which is 2 points. So when we start this discussion and we think about the average rate of change, we need to talk about where we are looking, and we're going to be looking between 2 points. And so it can be any 2 points that I give you, but for the sake of learning how to do this, we are going to look at what's happening between 1 and 3 for this example. So we are interested in the average rate of change, and I'm going to tell you what this means exactly, between x equals 1 and x equals 3. So I'm picking 2 points to illustrate what we're doing, but you'll see that we can look between any 2 points on a graph, on a function, all sorts of things as we go. This is just our starting example. So if we want to know how much the function changes between 1 and 3, right? So where's 1? 1 is here. Where's 3? 3 is here, right? My ultimate goal is to figure out how much I change between these 2 points, okay? Now, I don't know how to do that on a curved function yet. And so, like I said, the one thing that I do know how to do right now is find the slope of a line. So what I'm going to do is I'm going to connect the 2 points with a line, okay? And so I know that this is not the exact rate of change, right? Because the exact rate of change would take into account this curve. So when I connect 2 points on a nonlinear function with a line, that is the average rate of change, right? So that's where this word average comes in. So it's telling me how much I change on average without really taking into account huge fluctuations between the points. But that's okay, because for now, what I know how to do is find the slope of a line. Our goal is going to be to make it better, to figure out at some point how to get the exact rate of change. But for now, we're going to start with the average rate of change because we know slope. Okay, so to find the slope of this line, we need to do the change in y over the change in x. And the way we're going to write this in this class, we're going to use a and b to talk about the values we are looking between. So 1 and 3 are going to be our a and our b. So to get this slope, the change in y is going to be f of 3 minus f of 1, which means I'm plugging the 3 and the 1 into my function, divided by 3 minus 1. So change in y over change in x. I want to note that when you do change in y over change in x, it doesn't actually matter whether you choose the 1 or 3 to be first or second, as long as you are consistent on the bottom. So this is the same calculation as if we did f of 1 minus f of 3 over 1 minus 3, right? So notice I can either have the 3's first and then the 1's, or the 1's first and then the 3's. As long as you are consistent with that, then your change in y over change in x will be the same either way, okay? So if we go ahead and approximate this, all right, I guess we'll do this one since I have more space down here. F of 1 means I'm going to go to my 1 value and I'm going to approximate the corresponding y value. So it's right between 2 and 3. So that's going to be approximately, and I'm going to say 2.8, right? And then my f of 3 value means I'm going to go to 3. I'm going to come up here. I'm going to come over. It's just a tiny bit above 1, right? So something like here. So I'm going to call that 1.3, right? We don't need to be super exact right now, but in the general area of. And then on the bottom, we have 1 minus 3. Okay, so I have to do the work of finding these y values, and then I can go ahead and crunch this number. So when I subtract these, I get, let's see, 1.5 divided by -2. So I get negative 0.75. Now, a couple things I want to remind you about in terms of linear functions. When your linear function is going downward from left to right, we are expecting a negative slope. So when I got a negative answer, that makes sense. That matches the picture of my line, okay? And so what this tells me is that my function changes by negative 0.75 between 1 and 3 on average. So this word average is really, really, really important, because for what we're doing right now is we're doing an approximation. So this is our work to start with today. So we're going to be looking at how we fit in this line between 2 points to approximate what's happening on a curve, okay? So we're going to be doing this with graphs. We're going to be doing this with all sorts of things, but we sort of want to finalize some ideas about how we apply this formula, okay? So the formula that we're going to be using, if we were to think about this generically, right, we have 2 points. We're going to call those points A and B. Okay, so let's say A and B are the 2 points we are looking to approximate between. Okay, so that means there's always going to be 2 points given in the problem. And so then we're going to be doing the change in y, f of b minus f of a over b minus a. So again, this is just a way that we write slope, right? So it's the slope of the line that connects 2 points. That's where we're starting. And this is where we are trying to find the average rate of change. So let's do a practice problem here. Hopefully, we can practice doing some of these rates of change. So here is a curved function. Okay, this is the line that we found. So the line between 1 and 3. So it's the same representation. But now we're going to try to approximate 2 other average rates of change. Okay, so the first one we're going to try to do is the average rate of change from x equals 0 to x equals 2. And so I'm just going to draw on the picture where that line is so you can try to do an approximation. So that's this blue line here. And then we're also going to do an average rate of change, let's see, between x equals 0.5. And again, I'm going to draw this line in a second. And x equals 4.5. And so that line, I'll try to make this as straight as possible, is this one here. Okay. So what I want you to do is I just want you to look at this graph, think about what the y values are going to be at these points, and then apply our average rate of change formula, which again, I'm going to write up here. Let me straighten this out, which is going to be f of b minus f of a over b minus a. So again, we're finding the slope of each of these lines. So try that out. I'm going to give you just 2 quick minutes. So see if you can approximate from 0 to 2, and then from 0.5 to 4.5, think about whether or not you expect it to be positive or negative. I suppose, do you expect it based on what the line is doing? And then do your best to approximate. It doesn't have to be exact, right? But as long as you're in the right ballpark, then we'll be good to go. Okay, so take 2 minutes, try to approximate each of these average rates of change, and then we'll go through it together. Take about 30 more seconds to finish up whatever part you're working on. All right, so let's start with the blue line, the average rate of change between 0 and 2. So even before I begin my calculation, I see that my line is going in the upward direction. So I'm expecting my slope to be positive. I don't know what it's going to be, but I expect that whatever calculation I do, the number that comes out will be greater than 0. Okay, so again, I'm going to apply my formula here to find the slope. So I'm going to do f of 2 minus f of 0 over 2 minus 0. And again, if you do f of 0 minus f of 2, that's fine as long as on the bottom you do 0 minus 2. The way that I pick my values here is I always do B for bigger. So I just pick whatever the bigger value is. But if you did it in the other order, you'll get the same answer, and that's totally fine. So when I approximate these numbers, your approximation might be a little bit different than mine, but as long as you are in the same ballpark, that is fine. So f of 2, I'm going to come to the 2, I'm going to go up to where I hit. And again, I'm going to try to approximate what the y value is here. That looks pretty similar to the one I did before. So I'm going to use 2.8. Okay, if you have 2.7, 2.9, 3, something in that range, that's totally fine. You shouldn't have something like 30, right? It should be somewhere between like 2.5 and 3. Now, f of 0, I come over here to 0, I go up. That looks like it's directly on the 1, so I'm going to use 1 divided by, now on the bottom, I have 2 minus 0, which is 2. So I have 2.8 minus 1 divided by 2. When I crunch that number, I'm going to get 0.9. Okay, and again, I was expecting a positive number, so that's good. So here, my slope is approximately 0.9. So your slope, however you approximate, should be in that area, right? You might have 1, you might have 0.8, but it should be somewhere in that general area. Now, for my second line here, between 0.5 and 4.5, I see that my line is downward sloping, and so I'm expecting that the slope will be negative. Okay, so again, I'm finding the slope, so f of b minus f of a over b minus a. Okay, so I'm trying to approximate, what I'm going to get for values here. So f of 4.5, that's this one right here. This looks like it's directly on the line, so I'm going to use -1 minus, now at 0.5, I come up here, and again, this looks pretty close to being directly on the line, so I'll use 2 divided by, now on the bottom, 4.5 minus 0.5, it's going to give me 4. Okay, be careful with negative numbers. It's really easy to mess them up. So -1 minus 2 is -3. -3 divided by 4 gives me -0.75. So again, I was expecting a negative slope. I got a negative slope. So my approximation is -0.75. So that is my average rate of change approximation. That is how much my function changes on average between these 2 points, which means that for every 1 unit that I move in the x direction, I'm expecting to move down by 0.75 in the dependent direction. So I would go over 1 unit, down 0.75, over 1, down 0.75, over 1, down 0.75, right? That's what that is telling me, the average rate of change. Now, when we use a line to approximate the average rate of change between 2 points, so when we do this process, that line has a special name, okay? So that line is called the secant. Okay, so this is the secant line. And so when you hear someone say they're using a secant line, that means that they are using a line to find the average rate of change on a nonlinear function. So when you use the line in this way, we call it a secant. A secant line connects 2 points on a nonlinear function. Okay, so we've sort of visualized what this line is telling us, but we can find average rates of change on things that are not graphs, right? So when you have the graph, you can see the line, you connect it, but what if you have something that's not graphical, right? So we're going to try to extend this to other types of functions. So we want to find the average rate of change between 1 and 4 for the function x squared plus 3x minus 1. Okay, so what I want you to do is I want you to try to use that formula we talked about to find the slope f of b minus f of a over b minus a between the points 1 and 4. Okay, so I'm going to give you about a minute and a half, and set up your formula using that, and then use this function to calculate the values that you need to then crunch the number. Okay, try it out. Again, feel free to check in with someone near you, see if they're getting the same thing. It's always good to have a friend in a math class, and then we'll go through it together. Okay, take about 30 more seconds. All right. So whenever we're looking for average rate of change, and again, the keyword we're looking at here is average. So when you see that, you should think, oh, average rate of change. We're always going to be given 2 points. So our 2 points here are 1 and 4. So we can apply our formula, f of b minus f of a over b minus a, to find the slope between 1 and 4. And again, you can do the 1 first, f of 1 minus f of 4 over 1 minus 4. It's just a matter of preference. So the difference here is instead of approximating from a graph, we have this function, which means we need to find f of 4 by plugging a 4 into this function. So 4 squared plus 3 times 4 minus 1, right? We crunch those numbers. 4 squared is 16, plus 12 is going to give us 28, minus 1 gives me 27. I also need to find f of 1. So again, I'm going to plug that into my function. 1 squared plus 3 times 1 minus 1, right? That's going to crunch down and give me 3. So now I can plug those values into the top of my function for the dependent values. So f of 4 is 27. F of 1, we said, is 3, divided by, now on the bottom I have 4 minus 1, which is another 3. So 27 minus 3 gives me 24, divided by 3, which is going to give me 8, which means that if I were to draw this function and draw the line connecting 1 to 4, the slope of that line would be 8. So my function changes on average by 8 units in the dependent direction for every 1 unit I move in the independent direction. So that is my average rate of change. Okay, so that's what that looks like when we have a formula. That's how we take this average rate of change and apply it to a formula. So we also want to be able to apply it to a table. Okay. So suppose the table below is continuous and gives the data of a population P in thousands measured in years T since 1970. So let's take a brief moment to understand what this data is telling us, and then I'll give you a chance to answer the questions. So this population model is modeling since 1970. So at time equals 0, that is the year 1970. At time equals 10, that would be 1980. Time equals 20, that would be 1990, because this is years we're adding to the starting date. And then in terms of the population is in thousands. So in 1970, the population was 60,000. In 1980, it was 65,000. So we can see that the population is increasing over time. That's somewhat helpful because if you picture an increasing function and think about the slope of a line that connects them, right, we're expecting that slope to be positive. Okay, so there's 3 questions I want you to think about and answer in terms of this table. The first one is, what is the population in 1970? So that's just interpreting the information and making sure we understand how the table works. And then for part 2, what is the average rate of change from 1970 to 2000? So we have to identify where those dates are on the table and then find the slope between the 2 points. And then part 3, similar, find the average rate of change between 1980 and 2010. So again, we have to figure out where those dates are on the table and then find the slope between the 2 points by doing the change in y over the change in x. So think about what is your dependent and your independent variable. Okay, so I'm going to give you 2 to 3 minutes to try to work out these 3 problems. The TAs will sort of be around if you need any help. Feel free to check in with someone next to you, and then we will go through it together. Take about 30 more seconds. All right. So for part one, what was the population in 1970? We have to remember that T is telling us the number of years since 1970. So 1970 is going to be time equals 0. And so since we will need this for later, let's go ahead and write in the years that are down the table. So 10 years later is 1980. 20 years after 1970 is 1990. 30 years later is the year 2000. And then 40 years after 1970 is 2010. So those are the corresponding years. So if we want to know the population in 1970, we come down over here. So time equals 0. The population at time equals 0 is 60,000. Okay, so there's two ways you can write it. You can write it with the word thousand. You can write it out as the number. That's fine. But the idea is that we have to also remember that the units of the population are in thousands. So 60,000 in the year 1970, because that corresponds to time equals 0. Okay. The average rate of change between 1970 and 2000. So again, we need to look at what years those are on our table. So 1970 to 2000, right? So that's time equals 0 and time equals 30. So how would we write this in our formula? Well, we could do something like P of 30 minus P of 0 over 30 minus 0, right? F of B minus F of A over B minus A. I'm using P here just because that's what was given in the table. You could certainly still use F in your notes, that's fine. But I wrote the T that it corresponds with. You could also write, P of 2000 minus P of 1970 over 2000 minus 1970, because that also represents 30 years. So that's going to give you the same slope. Okay. So P of 30, the population in the year 2000, I come down here, I see that the dependent value is 85 minus P of 0. So we already looked at this one a little bit, but the corresponding population is 60 divided by 30. So I'm going to leave a little space because I'm going to write something there after. But when we crunch this number, right, 85 minus 60 gives me 25 over 30. If I turn that into a decimal, I get 0.8333, repeating, okay? But we need to sort of talk about what that means in terms of units for this to make sense, because we're talking about a population, right? And people, it seems weird to have decimals when we're talking about people, but let's think about what the units are going to be. So I'm going to write the units here. So on the top, we were talking about the population, right? So that's people in thousands. So we're going to just write people for now. We'll deal with the thousands over here. And then on the bottom, the 30 minus 0, that's the number of years. Okay. So since we're talking about the rate of change, we're talking about how many people per year is this population changing. And again, we have 0.833, but the population is in thousands. So it's actually 0.833 thousand people per year. Okay, so it's less weird when we recognize that it's thousands of people. You could also multiply this number by 1,000 and just say 833 people per year. It's up to you whether you want the thousands to be in words or if you prefer to turn it into a number. But we're talking about the change in population, how many new people we gain each year. I know that the population is growing because this number is positive. Okay, so doing something similar for part 3, the average rate of change between 1980 and 2010. So for me, I'm going to write this as P of 40 minus P of 10 over 40 minus 10, right? Because that corresponds to the years. I'm just using the T value. If you wanted to use the years instead, that's totally fine. So here, when I find the dependent value that goes with it, I have 100, and then P of 10 is 65 divided by, now 40 minus 10 is 30. So here we're going to have 35 over 30. And when we crunch that number, I get 1.16 repeating, so 1.167. And again, I have to include the units here for this to make sense. And I know that that's in thousands of people per year. 1,000 people per year. So that means I'm changing by about 1,167 people per year between the years 1980 and 2010. So every year I expect to gain almost 1,200 people towards my population. That's how much I change on average. Okay, so that's how we find that type of information from a table. Quick check again on the graphs. Here we're going to try to use the graph to find the average rate of change from 0 to 4. I drew in the line, take one quick minute, apply the formula just like we did in the first problem. We're just remembering back now that we're practicing. Go ahead and try that out for a quick minute. All right, so let's set this up real quick. So we're interested in what's happening between 0 and 4. So our formula, f of 4 minus f of 0 over 4 minus 0. So f of 4 we see is way over here. If I go to the corresponding y value, I have a value of 2 because we're up 2. So I have 2 minus, now f of 0 looks like it's at 0, close enough. And 4 minus 0 is 4. So I end up with 2 over 4, right, which is 0.5. I have a positively sloped picture of a line. I had a positive slope. That all seems very reasonable in terms of an answer. Okay, so that was just a quick check on the graph, since the first one we did, we did in a bigger context, but now we've done a formula, a table, and we've done another graph. Okay, so the next thing we're going to look at is a quick application of how we might see this in a context where we have to recognize that what we're looking for is the average rate of change. So we want to get used to looking at word problems. Oh, okay, I'll move that down a little. And so to start thinking about these word problems, we're going to start introducing some ideas from physics, okay? It does not matter if you've had physics before, you are not expected to know any physics, but we are going to be doing a couple of applications to physics, so we want to make sure that we understand the terminology that we're using so that we can do these types of calculations. So the two key things we're going to talk about right now are distance and velocity. So distance is going to be the measured length between two different positions. Okay, so typically we notate this with the capital S of T. So think about like the distance between you and the screen, right? So your position is position 1, the screen's position is position 2. You would measure the difference between the two. That would give you your distance. Okay, so we can measure all types of distances, some very close, some very far. And typically we'll have units of what we're measuring. Are we measuring in inches or feet or miles, right? The term that we're going to use that goes with this, that we're going to be looking at in the next problem, is velocity. And so velocity is a rate of change, okay? And again, we're going to be using average rate of change to think about velocity at first, but velocity is the rate at which your position is changing, okay? And so that is, again, approximating how this position function changes. And a common velocity that people are familiar with is when you drive, right? If you're going 60 miles an hour, that means your position is changing by 60 miles for every 1 hour you drive. So it's distance over time. So if we consider how quickly your position is changing, that's called velocity. So if you're walking at, 40 feet per minute, that is a velocity. So you hear that word per. So if you have a distance per time, that is a velocity. Okay. That being said, let's take a look at this example. Suppose the position of an object falling off of a building can be found using the formula S of t equals 2,704 minus 16t squared, where position S of t is measured in feet and time t is measured in seconds. So we're talking about feet and we're talking about seconds. First find the time when this object hits the ground, then find the average velocity of the object from t equals 3 and t equals 6. So what we're going to be practicing here is trying to understand how to apply what we're looking for to the information we have, right? So there's two questions. One about the average rate of change, so that's the average velocity. And we're also interested in trying to figure out how we determine when this object hits the ground. So you need to think about what that means, right, in terms of the information we have. So this is just sort of a first step in trying out some sort of critical thinking about how to apply what we know. So I'm going to give you about 3 minutes to try out this problem, see what you can figure out. Feel free to check in with someone next to you. The TAs will walk around, and if you have any questions, you can ask them, and then we'll go through it together. Okay, take about 30 more seconds. Okay, so the first question is a little bit tricky. This is where we're trying to bring in some critical thinking and trying to figure out what we are trying to figure out. So find the time when the object hits the ground. Okay, so we know two things in this problem. We know position and we know time. Those are the two related variables. If we are trying to find the time, that means that we need to know something about the position. That means we are solving for t. Okay, so that means we have to reason through what the position will be when the object hits the ground. So you might already know what it is, or you may not have figured it out, but let's quickly, I like to draw pictures to visualize what's happening. That helps me think. So let's imagine we have this building, okay, with some windows. Please excuse my not perfect drawing skills. Okay, so the position has to do with where that object is after it's dropped off the building. Well, right when you drop it, that's time equals 0, right? So we can kind of tell what the height of the building here is, right? So this is 2,704 feet is how tall the building is. And so if we want to know when the object hits the ground, the position when it hits the ground should be 0 feet, right? Because the position has gone all the way down to 0. So what we need to do to figure out the time when it hits the ground is set position equal to 0, when the position of this object has hit 0. So we have 0 equals 2704 minus 16t squared. Having position have a number allows us to solve for t. So I'm going to bring this term to the other side by addition. So 16t squared equals 2704. I'm going to divide both sides by 16. When I do that, I get t squared equals 169. I'm going to take the square root of both sides. So I get t equals plus or minus 13. Okay. Now I need to think about if both of these answers make sense or if only one of these makes sense. T is time of how long it's been falling. It doesn't make sense for time to be negative in this situation and in most situations. So I know that this is going to happen at time equals positive 13 seconds. Okay, so I'm going to hit the ground with my object after 13 seconds. Okay, for part 2, I want to find the average velocity. So average, that word indicates average rate of change of the object from 3 to 6. So this is where we bring in our formula, right? I'm going to use S because that's our governing letter here, but you can do F if you're more comfortable with that. So S of 6 minus S of 3 divided by 6 minus 3. The average rate of change formula, I've just adapted it with S because that's what I've given here, okay? Which means I'm going to plug in a 6 into this function. When I plugged in a 6, I got 2128 minus, now I'm going to plug in a 3. Let's see, when I get a 3, I get 2380 divided by 6 minus 3, which is 3. I'm going to talk about the units for a quick second. The units on the top have to do with the change in position, and position is in feet. So the units on top are in feet, and on the bottom, 6 and 3 have to do with the time. So that's 3 seconds, okay? So when I crunch this all in my calculator, I get negative 84, and my units are going to be feet per second. So my position is changing by 84 feet for every second in the downward direction. So that negative is going to tell us we're going down as we go. Okay, so that's how we might see this in application. We might see the word average in the problem, and that just indicates that we're doing average rates of change. Okay. Okay, so the next thing we need to talk about has to do with the shape of a graph. You may or may not have learned this at some point. So if you haven't, that's okay. And if you have, this might be a different approach to talking about it. So when we talk about graphs, there's 3 big categories that we use to describe graphs. The first 2, hopefully you know. So the first one is positive and negative. So when is the function positive? When you're above the x-axis. When is it negative? When you're below the x-axis. That's the first category, positive and negative. The second category is increasing, decreasing. So that was in the videos from last time, but a function is increasing if it's going up from left to right, and it's decreasing if it's going down from left to right. The third category is what we're going to talk about now, which is the concavity. So the concavity of a function describes the bend of a function. So a function that is not linear can either bend upward, that looks like a cup, or downward, that looks like a hill. Okay, so that's what we're talking about when we talk about concavity. So a function is going to be concave up if it bends in the upward direction, so it looks like a cup when you look at it from left to right. Turns out that another way we can determine concavity is by looking at the average rates of change as you move from left to right. So notice here that the average rate of change at the leftmost approximation I did was -5. Then I did another one, -3. I did another one, -1. I did another one over here, +3. The average rates of change as you move from left to right are going to be increasing when you are concave up. Okay, this is important because when we study functions that don't have a picture attached, we need a way to be able to determine how they bend. Okay, so we're able to use average rates of change to determine that by seeing if the average rates of change are increasing or decreasing. If they are increasing from left to right, we are concave up. Okay, as you probably could have guessed, if they are decreasing from left to right, and this is an example here, +5, +3, +1, -1. As I move from left to right, these are decreasing average rates of change. That leads to a function that is concave down. And concave down means it bends downward and it looks like a hill. Okay. So that means we can use average rates of change to figure out where things are concave up and concave down by looking at how those values change. Are they increasing or are they decreasing? So we're going to look at an example on how to apply this. So we have this table here that represents some sort of continuous function, and we would like to try to figure out where we think this is going to be concave up and concave down. So what I'm going to have you do is I'm going to give you about 2-3 minutes, and what I would like you to do is approximate the average rate of change between every 2 points. Okay, so you're going to be doing the slope, the change in y, or f of x, over the change in x. So you'll do 12 minus 10 divided by 2 minus 0. You'll get some number. And then you'll do 16 minus 12 over 4 minus 2. And you'll do that down the entire table. And then once you have those approximations, which are the average rates of change, we're going to look at where those are increasing and where those are decreasing. Okay? Where those are increasing, we are concave up. Where they are decreasing, we are concave down. Okay, so take about 2-3 minutes, do these approximations, and see if you can figure out where this function is going to be concave up and where it will be concave down. It'll be good practice doing these average rates of change. Okay, so take 2.5 minutes, and then we'll go through it together. Okay, take about 30 more seconds. All right. So here, when I approximate the average rate of change at each point, these are the approximations that I get. Hopefully you're getting the same thing. We'll just look at one together as an example. Here, this 2.5, I did 35 minus 30, which is 5. That's on the top, the change in y, divided by 10 minus 8, which is 2. 5 divided by 2 gave me this 2.5. Okay, so these are all average rates of change. Turns out we're going to be doing a lot of average rates of change on tables throughout this course. So we want to get really comfortable with doing this fairly quickly, right? Today's the first day, so yeah, but we'll get there. So now to talk about the concavity, I need to consider when these values are increasing and when they are decreasing. So 1, 2, 3, 4, that's increasing, right? And then 4, 2.5, 1.5, 0.5 values are decreasing, okay? So when my average rates of change are increasing, my function is concave up, which means it bends upward. When my average rates of change are decreasing, I am concave down, which means I am bending downward. Okay, This particular use of average rates of change to talk about concavity is something that's going to continue throughout the course. So this particular relationship is really important. So if you're taking notes, you may want to put like a star around it or something to indicate that this is something that's going to carry through this idea that when the average rates of change are increasing, we are concave up, and when they are decreasing, we are concave down. Okay, so that's how we approach that. Now, tying these ideas together, and to sort of remind you that we don't always have to do things super complicated if there's an easier way, we want to use the graph below and figure out where are the intervals where this function's increasing and decreasing. So where is it increasing? Where is it decreasing? Where is it concave up? Where is it concave down? Okay, so just in case you can't see it, this is 1, this is 2, and we're counting by 0.2 on the x-axis. And then here, this is the 1, this is -1, right? And we're counting by 0.5 on the y-axis, okay? So I want you to take 1 minute to try to just mark on the graph, you can draw a sketch of it, where it's increasing, where it's decreasing, where you see it being concave up, and where you see it being concave down, okay? This is a completely visual exercise. And just to remind you that some of these things we don't have to calculate for if we can see it. Okay, so take a minute to jot down what you think is happening. Okay, so hopefully you visually sort of tried to guess where these things are. So a function is going to be increasing when it's going up from left to right. So that appears to be happening here. Okay, we are increasing, and this looks like it's going from 0 to about 0.5. So we'll say for x between 0 and 0.5, I am not including the 0.5 because the point where we turn around is actually constant. Okay, so we don't use inclusive, we use the open interval notation. And then I'm also increasing here, right, going up from left to right, which looks like this is about 1.5. So for x between 1.5 and 2, I'm also increasing. Okay, decreasing, I'm going down in the part in between. So I'm decreasing from, let's see, 0.5 until 1.5. So my increasing and decreasing take up the whole interval once I put all the intervals together. So hopefully that's what you visualized. Now in terms of concavity, I notice here that I'm concave down the first half of the graph. So I'm just going to write CC down for concave down, and that happens from 0 to 1. And then I can see that I'm upward in the second half of the graph. So concave up from 1 to 2. And again, I'm not using the inclusion points. The point where we turn around right at 1 has a special name. And the point where you turn around, it's not concave up or concave down. We'll talk more about like what those points exactly mean later. But for now, when you talk about these types of intervals, we are using open interval notation. Okay, so again, we didn't have to calculate average rates of change here to talk about the concavity because we can use the visual definition. We had to do it on the table because we didn't have the visual. So that's when we do the calculations to use that relationship. Okay, so very quickly, we also have something called the relative change. And I would say that when we talk about rates of change, The average rate of change we use 95% of the time. We do have to mention relative change. It does come up every once in a while. So I just want to make sure there's a clear distinction between what relative change is. And so we'll do a quick definition in one example so you get the gist, and then you should be good to go. Okay, so relative change. Think about if you received a discount of $1 on some sort of product, and I ask you, hey, was that a good discount? Well, the answer is it really depends, right? So if you're buying a car, a $1 discount, not that great, right? You're like, okay, well, the car is like $1 million anyway, so getting $1 off, not a big difference. If you're getting an iced coffee and it's like $2.64 and you get $1 off, that feels like a really big discount, right? So the idea is that the change is relative to the price, right? So whether or not it's important or big is relative to where you started, okay? That's where the word relative comes in. So relative change, which is also sometimes called percent change, is used to compare two quantities while taking into account the size of the numbers being compared, i.e. the original amount. So what we're going to be looking at is still the change in Y, right? So how much did the dependent values change? But then instead of scaling it to one unit in terms of the independent variable, we are going to divide by the original amount to see what percentage we changed by. And that will tell us if it's a significant change or not. So the numerator is going to represent the absolute change between the two numbers, and we divide by the original amount. Okay, so what does this look like? So let's say we're buying a car, right? It's $25,000. And again, the dealership offers to sell it to you with $1 off, which again is not a very good deal. Let's look at the relative change. So the way that we're going to set this up, okay, is that we want to look at P0 and P1. So let me note this here. So P1 is the new amount and P0 is the original amount. Okay, for our formula. So here, the new amount is the deal, the $24,999, right? So we have $24,999 minus the original amount, $25,000. And we divide that by the original amount, because that's going to tell us the percentage that we changed. Okay, so here, when we calculate this, as you can imagine, we're going to get teeny tiny decimals. We get negative 0.0004. Oh, I missed some zeros. There's 1, 2, 3, 4 zeros. 1, 2, 3, 4 zeros, and then a 4. So what does that tell us? So that tells us, so we're going to move the decimal place 2 places over, and we get 0.00%, 0.04% decrease. So we are going to convert that negative sign into the word decrease. And this is the percentage by which our price has been decreased. So 0.004%. And again, in order to turn my decimal into a percentage, I need to move it over 2 decimal places. I think we can all agree that a 0.004% decrease for a car, not a very good deal. Okay, now let's compare that to the coffee, right? So again, this is the original amount, $2.64. So that's our P naught. Our discounted amount, or our new amount, is $1.64 because we're saving $1. So if we look at the relative change here, we're going to have 164 minus 264. And again, we're dividing by the original amount to see how much that changed based on the original amount. Okay, when we calculate this, we get negative 0.3788. So when we talk about this or we discuss it, we're going to move the decimal over and we get 37.88%. So by moving it over, and because it's a negative, we have a 37.88 decrease in price, right? That is a much better percentage off in terms of a discount. Okay, so it's relative to the price. So that's how relative change works. Again, we don't use that as much as average rate of change, but it does come up very occasionally. Okay, so try out the 1.3 homework. Try it out today so you can stop by Drop and Help. And don't forget to submit your homework and mini quiz for 1.3 by Sunday night. I will see you guys all on Tuesday. Have a great rest of your week.
That's